welcome back, boys and girls. It's your main mathematician coming to you live from Summit Academy. In this video, working on that unit number 7 still, but we're working on lesson number 8. We're talking about bringing all those ideas together, but we're trying to be able to use and explain a rule for multiplying terms that have different bases but the same exponent. And so let's try to see how this works. What we can do is, for this first one, it says to evaluate, and it says 5 to the third power times 2 to the third power. And what we can do is we can find out what each of these are, but we can say, well, this is going to be 125, and this is going to be times 2 to the third power, which is 8. And so altogether, I can multiply those two together to equal 1,000. Then I can say if I evaluate 10 to the third power, I can expand it out, and I can say that's the same as 10 times 10 times 10, which is the same as 1,000, because if I count out the zeros, I have 3 zeros. So both of those are going to be the same, even though they look different. And if you notice how I have, if I have 5 to the third power times 2 to the third power, again, those have the same exponents, but they have a different base. So you can say that you can multiply, so same exponents, but different base. If they look like this, we can multiply bases and keep exponent. So what we can do is we can say if we have 5 to the third times 2 to the third, that's the same as 10 to the third power. So in this table, it says that we're going to write the expanded form, which means we have that multiplied out, and it says we're going to talk about the products of expressions with different bases in the same exponent. It says complete the table to see how we can rewrite them, and we use the expanded column to work out and combine the factors into a new base. So let me get rid of this part right here. There we go. So that's going to be our full table. So what we're going to say is this: we have our expression on the left side, we have our expanded form in the middle, and we have our exponent form on the right. And so similar to what we just saw, we did 5 to the third power times 2 to the third power. They expanded it out. They rewrote it to group it together, so that way it's 2 times 5 in each of those groups, which each of those groups is equal to 10. And since we have 3 of those groups, we have 10 to the third power. So same idea I'm going to do for the next one. Since I have 3 to the second power times 7 to the second power, I can expand it like this. So I'm going to do 3 times 3 times 7 times 7, which is going to be equal to 3 times 7 times 3 times 7, which is the same as 21 times 21, which is how we get 21 squared. So then make sure you can expand it out and rearrange it so that way it works for those problems. So for the next one, same idea, we're going to do 2 times 2 times 2 times 2, because we have 4 of these 2's multiplied together. Then we have 3 times 3 times 3 times 3, because we have 3 to the fourth power. Now group those together. So we're going to say 2 times 3 times 2 times 3 times 2 times 3 times 2 times 3, which if each of those groups is going to be equal to 6. So we're going to say 6 times 6 times 6 times 6 is going to be 6 to the fourth power. So we're just combining and expanding out those different groups. So now let's work backwards on this one. If we have our exponent form is 15 to the third power, what we can do is we can write it like this. Let's say we have 15 times 15 times 15. So I'm going from exponent to expanded. Now I'm going to break apart these groups. So now I can say that's the same as 3 times 5 times 3 times 5 times 3 times 5, which is the same as 3 times 3 times 3 times 5 times 5 times 5. So make sure you can go from that exponent form to the expanded form and have those different groups. And we can say, okay, well, how many 3's do I have? Well, I have 3 to the third power times 5 to the third power. Same idea with the next one. Expand it out, so I have 30 times itself 4 times. Group them together so I can split this apart. You can also do 5 times 6 if you want to do it like that, but I'm just going to do base 10 since I like working with those base 10s. So I have 10 times 3 times 10 times 3 times 10 times 3, fourth time. And now I can separate those groups. So I'm going to say this is going to be equal to, I have 10 times 10 times 10 times 10 times another group of 3 times 3 times 3 times 3. So notice how I have those different groups. And so I can say that's going to be the same as 10 to the fourth power times 3 to the fourth power. So make sure you can expand those out. Moving on to the next one, I can say I have 2 to the fourth power times x to the fourth power. So what's this one going to look like? Well, let's expand it out. So we have 2 times 2 times 2 times 2 times x times x times x times x. So make sure it's working just like a normal integer would, but we don't know what the x value is, so we're just trying to do that general form. So this is going to be equal to, well, we can say, if we multiply those groups together, we have 2x in each of those groups, which is going to be the same as, in parentheses, 2x to the fourth power. So make sure you can multiply those bases together when they have the same exponent. And so let's now do, in green, we're going to do our, let's say this is the general form. So what we're going to say is like this. We have a times, and then dot, dot, dot. And we have b times, dot, 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 like that. So it's, however many b's we have to multiply them all out, and then we can group them together. So each of those groups is going to be a times b times however many we have, a times b. And what we can say is that's just going to be the same as a times b to the power of n. So when they have the same exponent but different bases, just keep the exponent and multiply the base together. And so lastly, I can do this 3-part one. Same idea. I can say I have 7 times 7 times 7 times 7 times 2 times 2 times 2 times 2 times 5 times 5 times 5 times 5. Which, if I have one of those groups, 7 times 2 times 5 is going to be equal to 70. So I'm going to say I have 70 times 70 times 70 times 70, which is going to be expanded out. I'm going to say that's going to be 70 to the fourth power. And for that last one, it says this. It says for number 2, it says what happens if neither the exponents nor the bases are the same? Can you write 2 to the third power times 3 to the fourth power with a single exponent? So we're going to say for this one, we're going to actually say if the exponents are not the same, then the factors cannot be grouped together evenly. So we're going to say no, this does not work. All right, and then towards the bottom of the page says select all true statements. So what we're going to do is write a couple things that we know down for this one. Well, since we have the same base, so this is same base, we're going to say add exponents. And so for this one, we would say this one's going to be true. Then similar idea for this one. For part B, we're going to say this one is same exponents. We multiply bases together. So we do 8 times 9 is going to be 72, so this one's also true. However, for part C, if we look at that one, they have different bases with the same exponent, So they should have multiplied the bases together. So we're going to say this one is false. We're going to say this is wrong, and it should be we keep the same exponents, but we multiply the bases. So we're going to say this is going to be equal to 72 to the second power, similar to what we had in part B. And then in part D, they should have just, this is going to also be false, when I say should have just added the exponents. So it should have been 2 to the power 17, which is that part A. So make sure you can see those examples. And then for number 2, it says find x, y, and z if 3 times 5 to the 4th power times 2 times 3 to the 5th power and times 2 times 5 to the 7th power is equal to x, 2 to the x, 3 to the y, and 5 to the z. So what we can do is we can kind of group these together. So what I'm going to say is this: group, same bases together. So I'm going to say I have 2 to the 5th power times 2 to the 7th. And I have times 3 to the 4th times 3 to the 5th, here and here. And lastly, our last group is going to be 5 to the 4th power times 5 to the 7th power. And so what you do is once you have the same bases, add the exponents. So we're going to say this can be equal to, well, I add together 5 and 7, so that's going to be 2 to the 12th power. Add together 4 and 5 to get times 3 to the 9th power. And then I add 4 and 7 together to get 5 to the 11th power. So what that means is this: we're going to say that x equals 12, y equals 9, and z equals 11. Moving to the back, it says Han found a way to compute complicated expressions more easily. And it says since 2 times 5 equals 10, he looks for pairings of 2's and 5's that he knows equal 10. For example, 3 times 2 to the 4th power times 5 to the 5th power is the same as 3 times 2 to the 4th times 5 to the 4th times 5. So what they did was they broke apart the 5 and they broke it into a 4 and a 1. And so then they can group it together and they can say, well, I have 2 to the 5th power, or 2 times 5 to the 4th power is the same as 10 to the 4th power. And then they did 3 times 5 is equal to 15. And then they solved that to be able to find their large number. So we're going to do the same thing. We're going to say we can break this apart or group this again. So we're going to say, let's do it like this. Let's say this is going to be equal to, and so I have 2 to the 4th power times 5 to the 4th power times 3, which is the same as 10 to the 4th power, 10 to the 4th power times 3 to the 3rd power. And so we're going to say that's going to be the same as 10,000 times 27, which is going to be 270,000. So just make sure that you're multiplying carefully with those. And then for the last one, a little bit trickier, but we can write some ideas down as well. So I'm going to say this is going to be equal to, so I can actually write it down here so it's easier to see. I'm going to say I have 2 to the 3rd times 2 times 5 squared times 5 squared times 2 times 3 squared times 3 squared all over 3 squared. And this actually cancels out on this first side because 3 squared divided by 3 squared is just 1. And so we can simplify. We're going to say this is going to be equal to, we have 2 to the 4th times, That's a 4 times 5 to the 4th times 2 times 9, because 3 squared is 9. So we're going to say this is going to be the same as 10 to the 4th times 18, which is equal to 10,000 times 18. So it's going to be equal to 180,000. All right, so same setup, a little bit trickier because there's a little bit more operations. We can do that same idea. Moving on to the next one. So it says the cost of cheese at 3 stores is a function of the weight of the cheese. And it says the cheese is not prepackaged, so a customer can buy any amount of cheese. And so since it says the function of weight, so we're going to say that the independent variable is going to be the weight, meaning the x-axis, and the dependent variable is going to be the cost, which is going to be the y-axis. And so it gives us some information. So it says store A sells cheese for $8 per pound, and store B sells the same amount of cheese for $B per pound, and a customer has a coupon for $5 off the total purchase at the store. And it says store C is an online store selling the same amount of cheese at C dollars per pound, but with a $10 delivery fee. Then it says this graph shows the price for stores A, B, and C. So we're going to have a couple different things to go along with this. So with this graph, it says match stores A, B, and C with graphs J, K, and L. So I'm going to say that store A goes with this line L, goes through 0, 0. And I say this store B goes with the line K because they have that coupon. And store C goes with that line J because we start at $10 no matter how much we buy. And for part B, it says how much does each store charge for the cheese per pound? We can say, well, the store A charges $4 per pound, store B charges $5 per pound, and store C charges $3 per pound. Then it says how many pounds of cheese does the coupon for store B pay for? Well, if we look at the graph, we start at that point 1, 0. So we're going to say that it is worth 1 pound of cheese. For part D, it says which store has the lowest price for a half of a pound of cheese. So we look at the graph, we say, okay, well, about half of a pound is going to be the lowest price. And well, we're going to actually say it's going to be store B because we can get $5 off our first pound. Then it says if a customer wants to buy 5 pounds of cheese for a party, which store has the lowest price? Well, we could find where those graphs on the x-axis where the weight is 5 pounds, so it'd be in between 4 and 6. And we'd say at that point is going to be where 5 pounds is at. And so it could be store A or store B would be the same amount for 5 pounds of cheese. And for that last part, it says how many pounds would a customer need in order to make store C a good option. Then it says if a customer orders more than 10 pounds of cheese, store C is the lowest option. And that makes sense because if you're looking at this point on the graph where 10 is actually at, we're going to look at that line J. It's saying that that line J is going to be lower than the other ones that we have. So make sure you can ask questions as they come up, and as always, super slam that subscribe button.